Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We'll start. Very pleased to have Drew visiting us from Columbia today. He's been working with John Wright on a bunch of non-convex optimization problems that are inspired by signal processing and computer vision and so on, and he has a series of some amazing results, really. So we're very excited to hear about them today.
Thank you, Alec. Yeah, I'm Ju, and I graduated from National University of Singapore in 2008, and then I spent 3 years doing research on computer vision, like doing object recognition, action recognition, all this stuff. And back in 2010, I was an intern in Microsoft Research Asia, where John Wright was there. And yeah, I was amazed by his research, and I decided to follow him. And then I moved to Columbia and do more theoretical work on, on problems inspired from signal processing, computer vision, and machine learning. And this talk is based on joint work with Wright and also my friend Qing Chu, who also has something to say with Microsoft because he just got Microsoft PhD research fellowship. So, okay. So all this line of research actually start from some experiment like 2.5 years ago. So what we did at that time is that we just pick a typical natural image. We extract a lot of patches from the image, and we convert the patches into vectors, and we stack the vectors into a big data matrix. Okay. And what we want to do here is we want to learn some compact representation for these patches, for this big data matrix Y. One way of looking at it is, okay, you just consider, try to factorize the matrix Y as Q and X, where Q we would like to call it dictionary matrix. The reason being that we want the column Q to be some representation basis that kind of resemble the typical Fourier or wavelet kind of basis. And X is the coefficient matrix. So for the purpose of doing image compression or image recognition, that kind of tasks, we normally want X to be as sparse as possible. So Q is the dictionary, X is the coefficient matrix, and we want X to be sparse. That's the task. So it's very natural to write down a non-convex formulation for this problem. Basically, we try to penalize the difference between Y and the approximation, and we want the coefficient to be as sparse as possible. For this simple experiment, we target at learning a orthogonal dictionary. That means it's square, and all the columns are orthonormal to each other.
What is O?
Yes? Oh, what's O?
The half. Doesn't seem like.
Oh, the half is just for, skew this a little bit.
But then lambda, you could just change lambda.
Oh, yeah, sure. That's not a, big problem. That's just, some convention, strange convention. Yeah, it's not a, yeah.
But what is O?
Oh, On is an orthogonal group. It's the set of all orthogonal matrices. So one interesting part about this formulation is that this map, Qx to Qx, is bilinear. So the interesting aspect about this bilinearity is that if you think of, suppose I can find a global minimizer for this optimization. Okay, suppose the global minimizer is here. And if I permute the columns of Q, that means I just exchange the order of the dictionary element. I can accordingly change the order of the coefficient. That means permute the rows of X, and I get an equivalent solution, right? So in the space, it's like I have another solution here. And you can imagine I have another, right? Because you have exponential many permutation possibilities. So the function in the space is definitely non-convex, right? You have isolated global minimizers at least. And of course, this assigned group is not convex. So this one is definitely not convex. But let's just try something simple. Let's just try, alternating directions. We just fix one and optimize with respect to the other. And we start from random initializations. We don't do any tricky things about initialization. It turns out for these two sub-problems, you actually get very simple solutions for, at least for this formulation. But that's not quite the point. The point is that what we did at that time is that we start with independent random initializations. We just, run the experiment for, say, 10,000 times, 10,000 iterations, and we repeat the experiment for like 100 or 200 different initializations. And we plot the final objective value in this figure. What's interesting about this figure is that it's totally not interesting because the function value is totally flat, which is quite surprising for us. Because if you think of typical non-convex functions, people, at least the picture in my mind is like, you will imagine something like this, right? So if I start from different point, just totally random different point, and I repeat many times, I will imagine that I actually get one thing that has higher objective value. But that's not the case here. And it's not coincident. Actually, you can repeat the experiment for many different images. I repeat the experiment for like 2,000 different images, just random selected, nothing special. I never observe any spike in the function value. So this is very intriguing at that time when I started to look at the problem. And we try to explain what happens, right? And especially for people who has some background in computer vision or object recognition, you normally run some non-convex formulations. You try to solve some non-convex formulations, and it's often the time that you get some good solutions. So this is very typical of that kind of phenomenon. So we try to explain what happens. But if you think of non-convex optimization at large, we do have a lot of non-convex formulations, for sure. But I know people really like this kind of functions, these bullshit functions, all kind of nice theoretical and practical things about it. And we will imagine typical non-convex function looks like this, or the 1D version maybe looks like this. And we believe it's hard. It's hard to find a global minimizer. And actually, from computer scientist point of view, actually you can prove even to computing a local minimizer is NP hard. So in general, it's hard. But obviously the gap is here, right? We observe something good, but we can't, our worst case theory can't explain it. So a natural question to ask is, what kind of non-convex functions are easy? And hopefully we can actually identify a subclass of structured non-convex problem that we can guarantee to solve efficiently. That's the hope here. And that's the target for our research. So the working hypothesis here is really that we believe that there are such kind of nice structured non-convex functions that has this kind of nice geometric shape such that you can actually design efficient algorithm to find a global minimizer. And without any special initialization. So we say initialization free here. We emphasize this word, initialization free. Okay. Later, I'm going to give several concrete examples on this. But before that, I would like to discuss what what I mean by this kind of nice structure. So we'll start with this, what I call X functions, because I don't have a good name for it yet. And then I'll give you very concrete examples from machine learning or signal processing that have this kind of structure. And I'll discuss briefly about what you can do with this kind of functions, to get a global minimizer. And I'll compare with other approaches to non-convex optimization nowadays. Okay, let's start with X functions. Before I give the definition, we can actually look at a very classic and old example of function that lie in that family. It's an eigenvector problem. Okay, you try to. This is a formulation you would try if you want to find the bottom eigenvector, right? You minimize this quadratic form and subject to the vector's unit norm. Okay. So let's make a little bit assumption on the eigenvalues. We just assume there are some gap on the top and on the bottom. Okay. In the between is fine. You can have equal eigenvalues. If that's the case, you can actually show that the only minimizer of this quadratic form on this sphere are the bottom eigenvectors. Okay. And the only maximizers are the top eigenvectors. What's interesting is the eigenvectors in between. They are saddle point. And they are typical saddle point. What I mean by typical is that it's a kind of saddle point you would imagine in your mind. It's really, you have some convex direction, you have some concave direction. So these eigenvectors have that kind of negative curvature direction. And this is a plot of the simple case where if my matrix is just this diagonal matrix, 1, 0, minus 1, obviously the top eigenvector is E1, the standard basis E1, and the bottom one is the E3. Here is the z-axis, actually. So this is a global maximizer. This is E1. This is the global minimizer. And this is the saddle point, E2. Okay. The reason it's a saddle point is that if you move in this direction, it's like this shape. And if you move in the orthogonal direction, it's the other shape. It's the convex shape. Okay. Okay, just from this example, at least we have two nice properties. One nice thing is that there are multiple minimizers, but they are equally nice, right? All local minimizers are global. And the second thing is that all the saddle points have some directional negative curvature. By that, I mean, for this example, I mean this one, okay? So if you have the first property, and if you want to do optimization, the task is only that so long as you can find a local minimizer, you are fine because local are global. So, and then the task is only how do you actually, get rid of this saddle point. You guarantee to escape saddle point. But anyway, that comes later. So P1 is pretty easy to understand, or local or global. The reason I want to emphasize P2 is this. Okay, so this is our typical picture of saddle point. Okay, we have this blue curve is the negative curvature direction. Okay, we do have complicated saddle point in high dimension. Actually, even in R2, you have this kind of saddle point. It is saddle point by definition, because by saddle point we mean in any neighborhood of the point you can find a value that's strictly larger and a value that's strictly smaller, right? So this is a saddle point, but that's definitely not the typical saddle point. This one arises because the first order and the second order derivative all vanish. The shape is determined by the third order derivative. So this function is actually x cubed minus y cubed. We will make some name for this kind of nice saddle. We'll call it writable saddle in the sense that you can actually write on that. And other people prefer a strict saddle, but anyway, I mean. for the purpose of doing optimization, I would like to augment P2 a little bit. It's P2 plus variant. So in this plus variant, besides the property that the saddle point has negative curvature, which actually is equivalent to that if you check the hashing has a negative eigenvalue. Okay, that's equivalent. Besides that, we make additional requirement on the other critical point. So we require all local minimizers to have positive definite hashing. Okay, so that means around the local minimizers, the function is strongly convex. Okay, that's the additional requirement on local minimizer. And
do you assume it's actually bounded away from zero, or do you just assume it's strictly positive definite?
Yes, if you want some concrete rate, you need to bound away from zero. Yes. And also, we make assumptions on the maximizers. So for all the other critical points, that means either saddle point or maximizers, the hashing has at least one negative eigenvalue. That means you don't have, for the maximizers, you don't have a pressure of maximizers. It's fine to have, maximizers that have the same value. It's fine to have the same value around this direction, but you still hope that you can descend from maximizers. So it's not totally a set of totally flat of maximizers.
This is like saying that everything is sort of first order.
Strictly first order? Why?
It's like saying you can. All you need is the first order, the first derivative in order to define the.
All the critical point. Yeah. Right, exactly. I make special name for function that only satisfy this P2. We call it writable saddle function, in the sense that this implies all the saddles are writable. You actually get infinite number of functions have this kind of property. That's the famous Morse functions. So Morse functions are the functions where at all the critical point, the hashing is not degenerate. That means the hashing is full rank. So you can actually check that implies these properties. That implies these three properties. Okay. Anyway, we don't want to get to the technical details, but the point is that we actually have many functions that verify these properties, at least. So yeah, this pertains to the question you ask. So for the purpose of derive concrete rate for convergence, we do need some quantitative control on these properties. So what these complicated expressions say is basically kind of stable variant of P2 and P1. So P2, sorry, this is only pertaining to the writable saddle property. So what it says are that either the gradient is large. Okay, if you look at the whole domain and any point in the domain, either the gradient is large, that means you are far away from critical point, right? Or if you are near any critical point, either you have a negative curvature, which you can verify by check this, hashing, this quadratic form, hashing acting on some particular direction, and show it's negative, okay? Or you are near to a minimizer, okay? And remember that we require around a local minimizer, the function is strongly convex. So you need to check that the hashing is positive definite here. Okay, so this is a quantitative version of the same thing, actually. Okay, so this is the most exciting part. I really want to bring in 2 or 3 examples that, okay, the first two are The first are worked out by us, and the third one is worked out by another guy. But these examples all give non-convex functions that verify the property we mentioned. Okay, so they all lie in this X function family. Okay, so I'll start with, okay, this is a reminder of the property we discussed. All local are global, and we make assumptions on this critical point. So the first one is sparse diction learning. I'm sure Alec is pretty familiar with that, and hopefully also other guys. So this problem has a far rich history than I can tell here. But the point is that actually our first experiment, remember our first experiment, that's actually diction learning. So at least we illustrate with some experiment. So the first paper, or at least the landmark paper in this area, actually published 2 decades ago in Nature, I think, by some neuroscientist. And then inspired by this paper, there are a lot of algorithm development in the past 2 decades. I think maybe even at least 100 of them papers on that. And interestingly, people have used this a lot for image processing, classically for image processing. But recently, actually, people use that for descriptive variant recognition, compressive signal acquisition, and also even they try to build some deep structure with this kind of diction learning. Okay, they use a dictionary to build their deep structure. That's pretty recent. So the problem here is really to understand whether we can do that. So a natural setting for understanding whether we can do that is consider this recovery setting. Okay, we assume that our data matrix is actually generated by some ground truth dictionary and some ground truth coefficient. And of course, we want this coefficient to be sparse, right? And the task here is that given y, can you actually recover this dictionary and this coefficient? Okay. So the model we study for this one is that we restrict the dictionary to be square and invertible. We call it complete. It's versus the normal definition of over-complete. Okay. And we assume this coefficient are based on Bernoulli-Gaussian law. So this Bernoulli actually decide whether this support is 0 or not. Okay, so theta here is critical. Theta actually control the sparsity level of the non-zero coefficient in this matrix. And this Gaussian law is actually not quite essential. So basically put some magnitude on the support. That's the point. So complete dictionary and Bernoulli Gaussian coefficient. Okay, they generate y. I only give you y. Can you actually get back to the ground truth? That's the problem. Okay, so one interesting observation when you make this restriction is that if this one is complete, by linear algebra, actually the row space of y is the same as the row space of x0. Okay, by row space I mean the row span. I mean the set of all vectors that you can generate by linear combination of rows of y. That's a row space. Okay. So this observation is actually very interesting because although you don't know x0, but this one says, okay, although you don't know that, you know the row space of x0 by knowing row space of y, because I tell you y, right? So, and since this theta is normally small, because we are interested in the case where x0 is sparse, when theta is reasonably small, it's like the rows of x0 are the sparse vectors in this row space, right? When theta is small, there are sparse vectors in this row space. And if you put a little bit additional assumption on the number of samples you have, actually you can prove they are sparsest ones. But anyway, I mean the point is only that we are given a subspace, and we want to find the sparse vector in the subspace. That's the point. And if you can find all the sparse vectors in this rule space, basically you recover x0. And then you can recover Q0 by solving this linear equation. Okay, so basically we reduce this problem to the problem of finding sparse vectors in a subspace. This subspace is given. Okay. So a natural formulation for this one again, we know that any vector in a row space of Y can be written in this form. So here, star is just a matrix transpose. So we want to find a vector that's hopefully sparsest one in this root space, but we don't want 0, right? 0 is definitely the sparsest one, but 0 is not interesting here. The point is that we want to find to be exact, we want to find a sparse direction, but we don't want 0, definitely. The hard part about this optimization is not about the sparsity itself, because for sparsity we have a whole lot of heuristic to do that. It's about this constraint. This constraint is very strange. It's kind of a non-homogeneous requirement on the coefficient on the optimization variable. One natural way of handling that is that we know that we only care about finding a sparse direction. So we can fix the scale of this one arbitrarily. So let's fix L2 norm to be 1. Okay, this is just a natural choice. And for L0, I'll just look at a natural L1 relaxation. Okay, so this is the non-convex formulation we'll study. It's non-convex because this one is sphere, right? It's sphere. Okay. So this is the non-convex formulation we want to study. And the way we'll study it is that we'll look at what this function looks like. What this function looks like on the sphere. This is a sphere. But the problem is that all the community tools we have for studying the shape of functions are by calculus. In calculus, you need to take derivatives, right? But this one is not nice. It's not differentiable. So for doing some analysis, we actually change the objective a little bit. What we really use for analysis is that we take a smooth approximation to the absolute value function. So this one is an absolute value function. We take the red one. The blue one is the absolute value function. We take the red one. The red one is a smooth approximation to L1, so to absolute value function. And it's infinite time differentiable. It's exactly this one. It's infinite time differentiable. And actually, it's also convex, but that's not quite essential here. The point is that we can now take derivatives. The reason we are so curious about taking derivatives is this one. So before we do any analysis, let's try to look at what this function looks like in low dimension. Okay. So what I plot here is that I assume here the dimension is only 3. A is only 3. And I send P to be infinity. That means I actually get like tens of thousands of samples generated by the random model. And I plot what this function looks like on the sphere. This is what it looks like. Okay. It's definitely not convex. It's very easy to find these local minimum others, different local minimum others. But it's interesting that although it's not convex, if you check the values, all these guys actually have the same value. So all these local minimizers are global. Okay. And these are the maximizers. And interestingly, you also have saddle point. So here, here, and here. They are saddle point because if you move along this direction, it's a convex shape. If you move along this direction, it's a concave shape. Okay. Again, they are writable saddle point. Yes.
So the reason why all the local minima are the same as the global minima is because they're kind of equivalent in their permutation transformation, right?
Not exactly. So here, okay, sure. So here you do have a symmetric copy due to the signs, right? Because we don't restrict the signs. But this one is negative, negative is hidden due to that reason. But this one, they correspond to different rows in X0. Remember our X0 have many rows.
Yeah, but you can permute the rows and then you still get the same.
Yeah, but they actually corresponding to different rows here. They actually correspond to different rows. Remember that we send P to infinity, right? So when this P is large,
Yeah.
our Bernoulli, remember our Bernoulli random model, Bernoulli Gaussian random model, that means the rows of X0 are almost equally sparse. Right? When P is large, you have infinite long vector. They are equally sparse. So they, and you know, the Gaussian, although they are Gaussian, but if it is infinite long and you look at the expectation, it's like, right, they actually produce the same function value.
So I think what Drew is saying, right, so he's currently looking at just one sample, one data point in some sense, right? This is the problem he's looking at corresponds to finding one sparse vector.
Yeah.
So one sparse code, and these two solutions correspond to sparse codes for two different images.
Yeah, yeah.
Right. So there are many different X0s that you can recover,
Yeah.
which are the different sparse codes, and those two solutions are
Right.
sparse codes for two different examples, which are both equally sparse, so the objective values are equal.
But I guess what I'm asking is, so you have Q and you have X.
Mm-hmm.
You define a permutation on Q and the inverse permutation on X, and get a different solution.
Oh yeah,
right?
yeah, sure.
And
But
are all
but
of these different
right.
solutions, just a permutation?
But that's
from-
just like, I mean, that's just like you actually transform the space. If you do permutation, that's just like you actually rotate the sphere in some sense.
Right. And
Yeah.
a rotation would leave this.
Yeah, yeah,
symmetry.
yeah, that's true,
But it
that's
seems
true.
like all the different solutions are just the different permutations, right?
That's not true. That's not true. That's not true. Yeah.
How do you see that?
So remember our y is, I guess I use q, right? Q0, x0. So here is a case where when this guy is infinitely long, remember, this guy is, you know, you get, you know, some value here, some value. For R3, we only have three rows, right? But when they are infinitely long, you can think of the sparsity level as equal, right? When these are equally long, because our model is Bernoulli times Gaussian, right? And if you evaluate the function values induced by these different rows, they are actually equal. Because in this case, it's like the expectation of something. Because they are infinitely long, you are effectively evaluating the expectation. But you know, they actually obey the same model, same probability model, so the function value should be equal. But
I don't get it. Why are there? So you have three different solutions here on this
Mhm.
sphere.
yes,
Why is it that a permutation can't take you from one to the other?
oh sure. I mean, permutation definitely can take you one to the other, but I mean, permutation corresponds to you actually rotate the function on the sphere. It's like you rotate this one to this one. Yeah, that's true. That's definitely true.
So all the different solutions are just permutations.
Yes. I mean, in that sense, that's true. It's like I take this section and I just rotate to here and paste here and copy and paste. Yes.
So I think this is related. I mean, the example you gave is where you sample an image and you come up with a matrix that is kind of overdetermined in some sense, right?
Yes.
So is there another example where all this would still be true if you didn't create such a redundant representation in the first place?
The example on image you mean the first experiment?
Sure.
Is quite different from what we analyze here. Remember, what we analyze is that we study this recovery setting. We assume our data matrix is generated by some ground truth dictionary and coefficient. And we assume some model on the dictionary and coefficient. This is very different from what I did in the first experiment. Yeah, I'm not claiming that's the case for real images. Okay, so any questions, any more questions on this one?
So you should have three, I mean, so coming back to John's
Mhm.
question actually, though, you should have three actually distinct, not related by permutation minimizers.
Oh, right. The reason here is they are exactly equal is because you assume P is infinity. That's the reason, yes. Yeah, there's a slightly technical point later on, but I don't want to mention it here because, yes, you are right, yes. And another way of looking at the function is that because it is on sphere, it's not so straightforward. Another way of looking at it is that it's symmetric. We actually take one of this guy. We cut the function via the equator plane, and we push the function onto the equator plane. Okay, so mathematically, it's corresponding to reparameterization of the function. So what I describe is exactly this. We take this one, they take the function value, and we just push down to the equator plane. Okay, so because this mapping is one-to-one, we just assign the value here to the corresponding point here. And this is what this function looks like if we do that. Okay, so here maybe it's more clear about the structure. So around one target point, the function locally is actually strongly convex. Okay, so around this target point is strongly convex. If you move away a little bit, the gradient is not zero. Okay, so if you move away a little bit, there are no critical point. And if you move away still further, you start to see this kind of saddle point. Okay, remember our readable saddle point? They are here and symmetric copies. But you have negative curvature in the third region. Okay, in the outer region. Okay. So, and of course, just now the plot is about when P is infinity. In practice, you want finite P. So what you care about in theory is really how large P need to be if you still want to have this qualitative aspect of the geometry. So we managed to prove that if P is n to the cube, up to some other factors, small factors. Actually, the finite sample version is also nice. Nice in the sense that qualitatively and also from optimization point of view, the same kind of nice geometry is there.
Is there a lower bound?
Sorry?
Is there a lower bound saying n cube as well?
You mean this complexity?
Yeah.
The lower bound should be at least n log n. So yeah, that's a big gap. But anyway, so this result is stated very informally, but the point is that we try to verify this non-convex formulation actually obey the properties we describe. You remember the X functions? All local minimizers are global. So here I would put a quote around global. There are technical reasons, but what I would say here is that they are not exactly equal in value, but they actually produce very good estimation for the thing you want to recover. Okay, there is a small technicality here, but you can think of that. Although they are not global, they are equally nice. That's the point. And you can verify. Remember, we put a stable variant of writability. You can verify that the function is also writable on the sphere. Okay. I won't discuss algorithm here, but I'll just say that by optimizing this function in polynomial time, actually you can do that, we actually get the first polynomial time algorithm for recovering complete dictionary, square and invertible dictionary, even when the sparsity level is linear in dimension. Okay. This is in comparison to previous work where you can only use efficient algorithm to get to very sublinear regime, or you can use inefficient algorithm to get almost to the linear regime. Okay. So that's what non-convex analysis and non-convex, formulation actually bring us. Okay, I have to speed up a little bit. So the second example is from signal processing. Maybe you guys are not quite familiar with this, but the mathematical problem is actually very neat. So phase retrieval, so basically you want to recover a signal from its Fourier magnitude. That's the problem. You do Fourier transform on a signal, you throw away the complex phases, and only the magnitude are remained. Can you actually recover the signal from the magnitude only? That's the problem. It sounds a little bit ridiculous, right? you throw away something and, But a lot of practical problems require this. Most of them are from imaging applications. This one is typical X-ray crystallography back to 60s or even 50s. There are new ones in astronomical imaging and microscopy. They need to solve this problem. So this is a formula. For a complex signal, given the magnitude of the Fourier transform, can you recover the signal? Okay. Hopefully this is neat, easy to remember. But in practice, people find that this problem is very undetermined, very undetermined. So people actually invent different kind of modification to the system design that hopefully give you some oversampling. Because it's underdetermined, you want to gather more information from the system. So one natural way is to do some oversampling. So people have different idea of how do you actually modify the physical system and do a little bit of oversampling. So mathematically, what people study are this called generalized phase retrieval problem. So for this complex signal X, and given the measurement of this form, I take a lot of linear measurement, but I only give you the magnitude. Can you recover the signal X? Okay. So the Fourier case corresponding to a case being the Fourier basis vector. Okay. So that's why it's called a generalized phase retrieval. And one intrinsic symmetry in this problem is that if you transform the signal by some global phase, that means if you add some phase offset to every element to X, actually the measurement won't change. So you can't recover whatever you use the global phase using any algorithm. You can't recover it. That's just the intrinsic symmetry, but it's fine. I mean, people are okay with that. And a natural formulation for this problem is that, it's like I give you a lot of equations. You want to solve the equations because I gave you this measurement and you want to get back to x. A natural one is least squares. Why not just try least squares? So this measurement, I minus the measurement, I minus this one, and I take the squared, these squares. You would argue that why not just use this one? I mean, why put a square here? Because it's not smooth. If you do that, the function is not smooth because if you expand the square term, the cross term is not smooth. That, invite a lot of trouble. So we prefer this smooth one. This is actually a fourth order polynomial in Z. It's a fourth order polynomial in Z. Okay. The nice thing about this problem is that although this one is very different from the previous example we look at, right? But it also has this kind of nice structure. The way to see it is, again, by plotting. You plot a low-dimensional picture first. So in this plotting, we assume the measurement vectors are Gaussian vectors. Okay, they are Gaussian vectors. And we assume the ground truth signal is just real. Remember, what we care about is actually complex signals, but here, let's just assume it's real. And we assume it's two-dimensional, so that we can plot something. And this is what this function looks like, what this fourth order polynomial looks like in a space. Or if it's not clear, I push the function down to the plane. This is the where I push the function value down to the plane, and you can see. So here, this point and this point are the global minimizers, are the thing you want to recover. Okay, around them, the function roughly looks like a convex. Okay, corresponding to these two shallow, valley. Okay, they are locally strongly convex. Around 0, so this is 0. The function is about concave. Okay, around 0, the function is about concave. And what's interesting is that you also get saddle points. So here and here. So here and here. So in this direction, the function is concave. Okay. In this direction, the function is convex. Okay. So although this is a very different problem, you still get that kind of structure. All local minimizers are global, at least from this plot. All saddle points have negative curvature. Okay, no curvature in this direction, in this direction. Okay. And you can actually show that for high dimensions, for complex signals. So this is the results we produce. So if the measurements are Gaussian, when the number of measurements is slightly larger than the degree of freedom. So remember here the vector is length n. So it's slightly, if you slightly oversample the signal with high probability, all local minimizers are global. So here are exact. Even we only have finite samples, here they are exact. And you can verify, you can find out the concrete parameters for this function being writable. Okay. Okay, we're almost there. So compared to previous work, people either do semi-definite relaxation. Well, they do get, qualitatively similar results. Although in some sense they are a little bit stronger, but computationally they are not attractive because normally normally here n would be number of pixels in an image. Remember in our application, I showed the image, right? So people normally want to extract image. N is the number of pixels in image. If you do SDP relaxation, you can hope to solve it. There are non-convex methods, but all of them are based on doing spectral initialization. That means you already put your initial point near the target, and then you do some local descent. Okay. So here, what non-convexity formulation or non-convex analysis bring us is that we actually prove that the geometry is so nice. If you have this many samples, you don't have to do any initialization. You just start from arbitrary point and you do not gradient descent, to be honest. You need to do something tricky, slightly tricky than that. But you can find a global minimum in polynomial time. Okay, so that's a contrast versus previous work. So here, the geometry is so nice, we don't have to do initialization. Okay, so these ones are based on the same model as ours, the Gaussian measurement. And interestingly, actually people care about more practical setting for phase retrieval. So here, the measurement model is very similar already to practical what people use in practice. Interestingly, you also have this kind of shape. We didn't prove it. We just plotted a low-dimensional picture, but it seems nothing is wrong. The qualitative aspect is still there. And other settings, in some senses, a little bit universal in the problem. Yes?
Just so I understand that, suppose you had an image and you took the Fourier transform.
Right.
And you just had the magnitude.
Yes.
Then each global minimum will be a different image, but they'll be equally good. That's.
Oh, no. So
minimum?
I can't guarantee for Fourier measurement yet. So here I emphasize the measurement is complex Gaussian. It's Gaussian. But what I believe to be true is this picture actually. So people suggest that although for Fourier measurement it's not nice, why don't we do this? We put a random mask in front of the image, and we switch the pattern for several times. Constant times is fine actually. So that amounts to a little bit oversampling, right? And then I do recovery. I believe that's true. That's exactly what I plot here.
So do you feel like each local minimum would produce a different image in that case? Or,
Yes.
but they'll all be equally good.
In value, in function value.
In function. Yeah.
Yes. They corresponding to you, I don't know,
Sure.
well, how do I describe that? Because you do a global phase transition to the image. So I have to skip the third one, I think, but it's actually the one that's from machine learning applications. The work by Shim Kalani, I think he also worked in Microsoft at least 2 years ago. He moved to Washington University, I think. But anyway, they work on tensor method for learning mixed level Gaussians, for doing independent component analysis, all kind of stuff. Basically, they reduce this machine learning problem to decomposition of nice structured tensor problem. Okay, and so this was about that. Actually, in these nice tensor problems, actually you have similar structure. Okay, I'll skip this one because I don't have time. I want to talk just briefly about the algorithm. Again, remember our nice geometry we studied throughout the talk. So all local minimums are global, and also all critical points are nice in some sense. Especially around the saddle point, I need the function to have negative curvature. The reason is that if you think of any optimization algorithm, especially first order method, if you are unlucky enough that you just sit on the saddle point, you take the gradient, you won't move, right? Because the gradient is 0. Yeah, of course, in practice, you almost never observe that. In practice, you are always lucky, but I mean, in theory, there is such a possibility. So the problem here is really how to deal with that situation. Okay, so the geometry we studied actually allows several possibilities. You can do several different algorithms with slightly different guarantees. The one comes with a stronger guarantee is this one, second order trust region method, which I'll briefly touch here. But I'll mention other possibilities. This one is collinear search, which basically is a second order line search algorithm. They use second order information. Stochastic gradient should be pretty familiar with people in the room. Even actually you can prove some result about deterministic gradient, but with random initialization. That's also possible, but I'll describe the second order method. Actually, it's pretty easy and pretty easy to see why it works. So if you think of a Taylor expansion around a saddle point, it's take this form. The linear term is gone because the derivative is 0. And if you choose the direction you want to move as the eigenvector corresponding to the negative eigenvalue, then it's very easy to see that you can actually decrease the function value, right? So yeah, that's the whole magic behind the second order method. And you can exclude saddle point via this method. Although, I mean, you argue that in practice, people never use second order method because it's expensive somewhat. So what we deploy here is so-called trust region method. It's a modified second order method. The reason that you want to modify it is that we know that sometimes we want to deal with indefinite hashing. That means hashing with negative eigenvalues. If you just run Newton method, that won't do it, right? Newton method actually only works for positive definite hashes. Or if there's 0 eigenvalue, Newton won't do it. You need to do some trick to Newton method. So one natural remedy to that is that why not do this? I just want to minimize a local quadratic approximation, but I restrict my movement to a small ball around the current into it. Okay, this is a ball. So this is called a trust region, and the whole algorithm is called trust region algorithm, trust region method. So the next interest is by the minimizer of this so-called trust region subproblem. Okay, that's trust region method. It turns out, remember for our dictionary learning example, we are actually minimizing a function over the sphere. So you need to do that. Just now the trust region is for unconstrained problem. It turns out that you can treat the sphere as a manifold, right? And you can generalize all the terms in trust region to manifold setting, especially for Riemannian manifold. That means manifold where you can define metric. You can measure the length of a curve. Okay. And you can do similar thing. So these are just technicalities. I would skip it. Okay, just briefly about how you can prove convergence. So remember we have 3 regions. One is either gradient is large, or there is negative curvature, or you are near a local minima where the function is strongly convex. So in the first 2 regions, you basically just prove that the function value decrease. Because the gradient is non-zero or the curvature is negative, you can always find a local descent direction. So you can decrease the function value. If you are near a local minimizer where the function is strongly convex, the second order method basically behaves like a typical Newton method. And you have this quadratic behavior. Okay. So the point I want to emphasize is that it's really that by this nice geometry and this kind of, at least for second order trust region method, you don't have to do any special initialization to get to the global minimizer. That's the point, okay, and efficiently. So these concrete theories are worked out in our papers, but there are some possibility of doing first order method in other papers. Okay, just briefly comparison with other approaches to non-convex problem. So one very attractive approach is doing convex relaxation. I think although people here are not doing compressed sensing that styles work, but you must have heard of compressed sensing, L1, nuclear norm, that kind of stuff. So in the last decades, there's this line of beautiful work about when can you recover signals with structures. If you want to promote sparsity, you should do what, that kind of stuff. The problem is that in this applied field, machine learning or signal processing, we know the case where in some case, even you have this kind of convex relaxation, you can't do optimization against that. That's one scenario. Another scenario is that you can do optimization with that, and the problem is that you can prove that they will be suboptimal in the sense that you need more than necessary to do that. So these examples are the second category. So in all these cases, we know some fundamental limit of convex relaxation. Okay. And another attractive approach is that, also very natural. I want to find this one, and I start from some point that's near to this one, then I, do local gradient descent. Yeah, that also works for many examples actually. Also very attractive, and even very practical actually. The problem is that for many problems, you don't know how to do initialization, especially if there's no probability assumptions on the data model. You don't know how to do initialization. And I think in practice, people never do clever initialization because you don't know how to do that. So at least I believe that don't explain what happens. And that may not be, I won't say wrong approach, but may not be the optimal approach to non-convex optimization. But anyway, I mean, even little theoretical understanding is better than nothing. Right? So what we do here is really we study what the function looks like in high dimensions. Just like a freshman calculus. We just basically study like derivatives and do analysis. And the nice thing is that even you stick to doing initialization, the geometry will still help you. I mean, whether you want to do initialization is fine. The geometry definitely will help you. And especially you don't have to. I mean, you can just use random initialization and the second-order method, and you're fine. Yeah, that kind of close my talk. And I thanks my advisor, John Wright, and my friend, Qing Chu. And these are the papers that I wrote in the past 2 or 3 years that the talk is based on. Yeah, and thank you. Thanks to all of you, and nice questions. And yeah, thank you.